and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will continue the discussion on the phenomenon of reflection. This time we will look at a concept called as total internal reflection, which is very important for optical waveguides and optical fibers. So, propagation of light inside optical fibers is governed by the phenomenon of total internal reflection. You might be familiar with the concept of total internal reflection from earlier physics courses or optics courses, but this time we will look at it a little more detailed and to see what happens when light is totally internally reflected onto the first medium. So, we can work with either TE polarized light for this or TM polarized light for this. We will arbitrarily choose the TM polarized light, okay, in order to show you the concepts of total internal reflection, but please keep in mind that the total internal reflection phenomenon is independent of which polarization, that is both polarizations exhibit the phenomenon of total internal reflection. But before we can discuss that, we have to do a little bit of a preliminary study to clearly bring out the notion of total internal reflection. We begin by looking at the reflection coefficient of the TE modes. Okay. So, we know that the reflection coefficient gamma of the transverse electric modes, we have shown you the expression in the previous class, is related to the medium impedances eta 1 and eta 2. So, this is obviously the medium with the impedance of eta 1 and this is a second medium of impedance eta 2, and light is incident at a certain angle theta I and exits into the medium at an angle of theta t. There is of course a reflection also, and that is precisely the the ratio of the reflected light to the incident light is precisely what this gamma t is telling us. Okay. So, the reflection coefficient expression for the case of TE polarized light is given by eta 2 secant theta t, where theta t is the angle of transmission into the second medium with respect to the normal to the interface, eta 1 secant theta I. Okay. So, since these are pretty close, let me erase this, but I hope that you have the picture of reflection in mind that we are talking about. So, divided by eta 2 secant theta t plus eta 1 secant theta I. Okay. I want to rewrite these equations in terms of the refractive index. Now, I can do that provided the media that we considered, both medium 1 and medium 2, are non-magnetic in nature, and since we know that for any medium which is non-magnetic, eta is given by square root of mu naught divided by epsilon 0 times epsilon r. This can be rewritten as eta 0, which is the impedance of the free space medium, divided by small n. This small n is the refractive index, which we have seen from the previous module to be related to the relative permittivity as square root of epsilon r. So, this eta therefore is inversely proportional to the refractive index of that particular medium. In the expression for gamma t, therefore, I can rewrite this as secant theta t divided by n2 minus secant theta I divided by n1, and do the same thing for the denominator as well, replacing eta by eta 0 by n and cancelling eta all the sides will give me this expression. Sorry, this is secant theta I, secant of theta I divided by n1. Now, I can readjust the equations, and knowing that cos of theta is equal to 1 by secant of theta, I can write these expressions in terms of cosine of angles, whether it is the angle of incidence or the angle of transmission. I would like to rewrite these equations in terms of cos theta t or cos theta I. So, I will leave this as a very small exercise for you to carry out, and the resultant will be very useful for us and will be written, the reflection coefficient will be written entirely in terms of the refractive index n. So, please note that this is the refractive index n that we are talking about of the first medium. So, n1 cos theta I minus n2 cos theta t divided by n1 cos theta I plus, sorry, again it is very easy to get confused between eta and n. I am sorry for the poor choice of notation, but this is a standard notation, so you will have to deal with this. So, n2 cos theta t. Anyway, does this equation make sense? So, does it make sense in the case of a normal incidence, the angle of incidence is equal to 0, therefore, the angle of transmission is also equal to 0. So, if you substitute theta I equals 0, theta t equals 0, you get n1 minus n2 by n1 plus n2, okay. And this is something that you should know. If epsilon r of the second medium is larger than epsilon r of the first medium, this means that the refractive index n2 will be larger than the refractive index n1, okay, and eta being inversely proportional to the refractive index means that eta 2 will be less than eta 1. Because the impedance is scaling inversely proportional to refractive index, the second medium will have a lower refractive index than the first medium. So, this equation certainly makes sense, because if you consider the scenario where eta 1 is larger than eta 2 and then you go from first medium to another medium, or rather if you go to the case where eta 1 is less than eta 2, okay, and you go from first medium to the other medium, or rather we consider the same case. So, eta 1 is greater than eta 2 and we are in this second medium having an impedance of eta 2, and when you shine light at normal incidence onto this one, the corresponding reflection coefficient will be negative, because you are now kind of terminating a transmission line with a higher characteristic impedance with a load impedance which is less than the characteristic impedance, okay. So, because of that the reflection coefficient will be negative, and that is precisely what this equation is telling us. Therefore, this equation as of now looks fine and we will continue to use the equation. Now, before we can use the equation, there is one small thing that we need to do. I do not want to use this theta t, I do not want to keep theta t in these expressions. I want to replace this theta t or equivalently cos theta t in these expressions in terms of the angle of incidence, because I would like to vary the angle of incidence and then try to see what happens to the reflection coefficient of this t wave, okay. In order to do that, I will employ Snell's law, which tells me that refractive index n1 times sin theta I must be equal to n2 sin theta t. Therefore, sin theta t, sin of the angle of transmission, is given by n1 by n2 sin theta I, and since cos theta t is equal to square root of 1 minus sin square theta t, this can be rewritten as 1 minus n1 square sin square theta I divided by n2 square, okay. This is an extremely useful relationship to keep in mind, and we plug this relationship back into the expression for gamma t e. Therefore, my new expression of gamma t e, which is a function only of theta I, the angle of incidence only, assuming that n1 and n2 are constant of course, is given by n1 cos theta I minus n2 into cos theta t, which is nothing but 1 minus n1 square sin square theta I divided by n2 square. This whole lot in the denominator will be n1 cos theta I plus n2 into square root of this quantity, okay. So, the square root actually covers the entire argument, okay. So, please note that one. Now, we consider two cases. In case 1, we have a situation where n1 is less than n2, that is your medium of incidence has a lower refractive index than the second medium which has a higher refractive index. This is a common situation that you would encounter if you take a tub of water and put a pencil in that and then look from the top, because air has a lower refractive index than water. This is a situation that you commonly see on a daily basis kind of a thing, right. So, let us see what happens to the magnitude of the reflection coefficient, right. So, what happens to the magnitude of the reflection coefficient as we now vary the angle theta I. What is the limit over which I can vary the angle? Well, this is one limit where theta I equal to 0, which is of course what we call as the normal incidence, and at the other end you might have the light incident or the electromagnetic wave incident just in the grazing angle or in the surface, along the surface of the interface, okay. So, this will have theta I equal to 90 degrees and this is called as the grazing angle, okay. So, you are just grazing the surface along like that. So, in these two extreme cases your gamma TE magnitude should vary. Okay. Obviously, when you consider theta I equal to 0 and n1 less than n2, the actual value of the reflection coefficient will be negative, but it would still be a real number. A negative real number is what you get when theta I is equal to 0. You can easily verify that from this expression. In the normal incidence, this is n1 minus n2 by n1 plus n2, n1 is less than n2, therefore this will be equal to some number, and that number is n1 minus n2 divided by n1 plus n2. Whatever that number is less than 0. But we are not interested in the actual value, we are only interested in the magnitude. Therefore, the magnitude of this quantity is greater than 0. Of course, if n1 and n2 are wildly different, that is n2 is say 100 and n1 is just 1, which is the lowest possible value that you can have, this magnitude will also be quite approaching 1, because n2 will be much larger than n1. So, you can kind of remove n1 from numerator and denominator relation to the value of n2 there, and the value of gamma TE will be approximately equal to 1. This kind of makes sense, right. So, if you put in a very high refracting material out there or material, then most of the light that you would incident would actually have to come back, right. Why would that be? I mean, you have a large value of the refractive index, which means there must be an even larger value of epsilon r, which is the relative permittivity, which means the impedance eta would be very, very small. So, very small impedance value means it is almost like a short circuit in terms of the transmission line. This is like a short circuit termination, and for a short circuit termination, the value of the refractive index will be, the reflection coefficient will be 1 in magnitude at least, right. So, we will not go to the extreme cases, we keep the values of n1 and n2 reasonably separate, I mean reasonably close to each other. Okay. So, magnitude of gamma TE as a function of the angle of incidence, okay, if you plot gamma TE looks something like this. So, at theta I equal to 0, it begins with some small value, but a positive value because you are looking at the magnitude. And what will happen at theta I equal to 90 degrees? Well, you go back to this expression. When theta I is 90 degrees, cos of theta I will be equal to 0, right. So, this term is gone. Similarly, this term is gone. What happens to sine square of theta I? Well, this would be equal to 1, this would be equal to 1. Okay. So, this is 1, this is 1. So, now we have minus n2 square minus n1 square under root divided by n2, the whole thing divided by n2 into square root of n2 square minus n1 square divided by n2, n2 cancels on numerator and denominator, and furthermore this will be equal to minus 1, and if you actually look at this, your absolute value would approach 1. Okay. It makes sense that this would be the case. So, if you plot it at theta I equal, so this was at 0, so this was at 90 degrees, I am expressing everything in terms of degrees here, the corresponding value here would be equal to 1. So, the magnitude of the reflection coefficient goes something like this. Okay. It is kind of monotonically increasing and of course reaches 1 at theta equal to 90 degrees. This is the so called grazing angle. In fact, you can show what the grazing angle is. If you take this piece of paper and if you look from the top, what you are doing is you are actually looking at it in the normal incidence, right. So, this is what you are doing in the normal incidence, but if you actually hold up the paper and then look at your eye level, what you are doing is essentially the grazing angle, and you can actually feel that almost nothing is seen, you can't see much of it if you keep it close to the eye, because most of the light is actually getting reflected. Okay. So, this grazing angle thing is something that you can actually try it out with a piece of paper, but the absolute value of gamma TE for the case when n1 is less than n2 will monotonically increase in this way. So far there seems to be no surprise whatsoever what is happening. Now we come to the interesting case. In case 2, we consider n1 to be greater than n2, right. So, you have maybe glass or you have water or you have some other material as the first medium, and then as the second medium you have air. Okay. Now light is incident at some angle theta I, and we want to see what happens to the transmitted and reflected angles. Sorry, this is theta I as well. Okay, so there will be reflection, there will be transmission, but now let us start varying theta I from 0 to 90 degree and see what happens. Okay, we go back to the expression that we had. I will rewrite the expression for your convenience. So this is n1 cos theta I minus n2 square root of 1 minus n square sin square theta I divided by n2 square. Okay, so I will just write it in this way. In the denominator also you have n1 cos theta I plus n2 square root of 1 minus n1 square sin square theta I, this expression, right. Now as I start increasing at theta I equal to 0, there is no problem, right. You will get the same n1 minus n2 by n1 plus n2, but this time at theta I equal to 0, the magnitude of gamma TE will be greater than 0, but the actual value of gamma T will also be greater than 0, that is, it is real but it is positive. Okay. Now as I start increasing theta I, something very interesting happens to the argument in this square root, right. Please remember, we are considering the scenario that n1 is larger than n2, okay, and this n1 square sin square theta I, let me sketch that for you. Okay. If I just sketch n1 square sin square theta I for you, okay, let us say n1 is equal to 3 and n2 is equal to 1. Okay. So 3 times sin square theta I, or rather 3 square, which would be 9 times sin square of theta I. As we start sketching this, at theta equal to 0, this would be 0, the quantity n1 square sin square theta I will be equal to 0, and you go only up to 90 degrees, right. So you start at 0 and then you keep increasing. At 90 degree, what is the value here? This would be equal to 9, correct, theta I equal to 9. However, let me draw a line of n equal to 1 for you. Let us say this is the n equal to 1 line. What do you observe here? For this region, as long as you are less than some critical angle, which we will call as some theta IC, the product n1 square sin square theta I will be less than the blue line. Since it is less than the blue line, then 1 minus of that quantity will also be, since the numerator is less than the denominator, right. So this quantity in the brackets will be less than 0, not less than 0, that would be less than 1, and 1 minus some quantity less than 1 will be some non-zero value, and everything seems to be going okay, right. So the absolute value of gamma TE starts, let us say we consider the same n1 and n2 difference here, it will again start with the same way, but it would slowly increase here. Okay. So maybe let us say this is what it would increase. Okay. Now at some angle theta IC, which we have calculated just now, right, I am not showing them to be on the same line, just to kind of bring out what is happening with the difference out there. Okay. So I am just trying to show you that these two lines are different, that is just for our own purpose. Okay. So it starts at some point which is positive, but then it kind of starts to increase, right. At this point theta IC, something happens to this n1 square sin square theta I. The green curve is no longer below the blue curve. Okay. In this region, this entire region, this term n1 square sin square theta I becomes greater than n2 square. So when this is greater than n2 square, what will happen to this square root thing? This will become an imaginary number. The integrand, the radical under the square root sign becomes an imaginary number, okay, which makes this gamma TE, the value of gamma TE, to be a slightly different quantity. In that case, what I can do is, I can, since I know that this quantity will be greater than 1, I will readjust the quantities over here. Okay. I will readjust the quantities by writing this as n1 square sin square theta I divided by n2 square minus, sorry, this is actually 1, but because I put this minus and plus over here, there will be a complex number j there, right. So I will have a similar complex number in the denominator. Again I will have n1 square sin square theta I divided by n2 square minus 1. Of course, n1 square sin square theta I is larger than n2 square only when theta I is greater than theta IC. So only after the so called critical angle, then n1 square sin square theta I is greater than n2 square, and which makes us to rewrite this gamma TE. Okay. So this is only when theta I is greater than or equal to theta IC. okay, only in this region when the green curve lies above the blue line. Now, does this equation not tell you or remind you of the form, let us say alpha minus j beta by alpha plus j beta, where beta is this quantity and alpha is just n1 cos theta I? Yes, it does, right. And what is the magnitude of this one? The magnitude will be equal to 1, but there will be a phase relationship here, right. So, the phase will be tan inverse of minus beta by alpha, right, divided by tan inverse of beta by alpha. So, you actually get minus 2 or rather 2 tan inverse of minus beta by alpha. So, there will be a phase relationship when theta I is greater than theta IC, but the magnitude of gamma TE will be equal to 1. Okay. So, the curve does something very interesting. The curve after theta I equal to theta IC breaks up and suddenly shoots up in magnitude and remains equal to 1. Okay. So, it suddenly shoots up in magnitude and remains equal to 1. Sorry, this was not clearly written. Let me write it. Let me rewrite this line. Sorry again. So, this is what happens at theta IC. Okay. So, this is what happens at theta IC, whereas the other case started off smoothly and eventually kind of very gracefully approached 1. Okay. This was the case when n1 is less than n2, and the red case is when n1 is greater than n2. Now, what is the meaning of the reflection coefficient becoming unity and staying unity for all the values there? That means the entire power is actually getting reflected back. So, the light, instead of getting transmitted into the second region, is now completely getting reflected into the first medium. So, no light, at least at this point, seems to be that there is no light in the second region, right. So, this phenomenon in which once the angle of incidence becomes greater than the critical angle, that there will not be any change in the I mean the entire light would actually be reflected back into the first medium, is called as the total internal reflection. Okay. So far we have written for TE case. Does this theta IC depend on TM case? Well, no, right, because cos theta T cos theta I never dependent on whether you were sending initially a TE light or TM polarized light. Even when you learned the concept of critical angle, Snell's law, none of it was discussed with respect to a particular polarization. Yes, the way gamma TM changes as theta I changes is completely different from the way gamma TE changes, but in terms of the critical angle and what happens beyond that, both polarizations will lead to the same condition, that light is actually reflected back. At this point, let me just write down what will be the scenario for the case of TM, gamma TM condition as I start varying theta I. Okay. So, let us assume again that at this point, we are on this one. Actually, as theta I changes, at some point the reflection actually starts to go down, eventually reaches 0. Okay. So, which means that is a very special thing that is happening when reflection is 0, that means there is complete transmission into the second medium, and then suddenly after this point shoots up to 1. This is a very interesting scenario, right. So, why is that in the TM case this reflection coefficient is going to 0? Well, there is a very special angle called as the Brewster angle, and this Brewster angle is given by the tan of Brewster angle is given by n2 by n1 of the medium refractive index n2 by n1. We will not derive it, but you can use this result, and this is true in general only for the TM case, because we are assuming. Okay. So, for such a two non-magnetic media, only TM polarized light exhibits this phenomenon of Brewster angle, where the angle of incidence equal to the Brewster angle, the entire light is transmitted into the second medium and nothing actually comes back into the first medium. This phenomenon of Brewster angle is used in many applications. One application is what we call as polarization upon reflection. Okay. Suppose I incident light at the Brewster angle. Okay. And let us say this light has a combination of TE as well as TM. So, this is coming from some unknown source. Okay. And I as of now do not know what is the amount of TE present in that, what is the amount of TM present in that. In general, it contains both components, let us say. Now, if it is possible for me to vary the angle of incidence, right, and I make it fall onto the second medium having a refractive index of n2, the first one having a refractive index of n1, if I decide or if I determine what is the Brewster angle and then let light come into that angle of incidence, then what will happen? Because of the Brewster angle, the TM component completely transmits, whereas the reflected component will have only TE component, whereas the transmitted component will not only have TM because of the complete transmission, but there is also a partial transmission of TE. Therefore, in the transmitted case you will have both TM and TE polarization, but in the reflected case the light is uniquely only polarized along TE. So, in fact, what you have done is to kind of separate out the TE and TM polarizations, right. So, you have separated the TE and TM polarizations by actually employing reflection phenomena, and whatever the light that is reflected will be polarized only along TE. In fact, this is used in laser cavities. So, you have in the laser, okay, instead of having these mirrors kept in this particular way, okay. So, let us say we keep a mirror in this or we keep a mirror here, instead of keeping a mirror like this, if you keep a mirror such that the light that is incident, okay, is at an angle of Brewster angle. So, this is the normal to the light, okay, this is the mirror actually that we have kept, and this is the light. Let us say this is a two-way mirror, or maybe I keep one more mirror at this point, okay, do not worry about that. So, this is the normal. So, you have a theta IB going in and coming back, then what happens? The light that gets reflected, right, will only be polarized along TE direction. So, the transmitted light will be TE plus TM, but the reflected light will only be TE, and in fact this light is the one that would further be transmitted and reflected back, okay. I am not showing the entire way in which this is done, but if you do this in the way, and therefore what happens after about a millions of round trip propagation is that the TE component gets selectively amplified, because that is the one that is reflected and keeps coming back and back, while the TM component keeps transmitting into the second medium and completely loses its amplitude. So, essentially what you have done is to obtain a very nearly single polarization light from the laser cavity, okay. So, these windows or these mirrors which are kept at the Brewster angle such that all the incoming light is at the Brewster angle is called as a Brewster window, and these are extremely useful in separating out the polarization, in selecting a particular polarization, and in suppressing a particular polarization. So, in all cases you are suppressing the TM polarization while selectively taking out the TE polarization. So, this is what we see, at least in terms of the total internal reflection and the phenomenon of total internal reflection and the Brewster angle. We have not derived or we have not shown that this angle theta I see to be the same for both TE and TM polarization, but it is very obvious. You just have to replace these expressions for reflection coefficient in terms of the TM and carry out a very similar analysis, okay. So, thank you very much.